here. There we go. Come on.
Oh, let's see. You're still there? Oh. Let's see. I think I lost you there for a second. I don't know if you're back now.
Yeah, I think. I went out for
yeah,
a second.
I see. Yeah, I see the chat now. Okay, yes, I do have that. Okay, let me just get that into position. Okay. That's right. Okay. Yeah. I remember we looked at this a little bit. Okay. Yeah. So I think you said, I mean, because I think I said like, all right, I know what a flop is, right? A floating point operation. I'm
Yes.
not like a super familiar with this multi-head self-attention, but did you say that they had given you like they had like lecture notes with
Yeah,
some definitions
I
of this
forgot
stuff or something?
I forgot to send those.
Yeah,
Yes.
because I'm sure we can like work it out. Let me see if I just like search around for that multi-head self-attention. Oh, that's right. You said this is like all PyTorch stuff.
Here we go.
Oh, okay. I see the other attachments there. Let me pull those up as well. Okay. Oh, okay.
What, I can't download these?
Let me take a look there. You should be able to. Let's see. If you hit the dot 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 menu, is there a download link in there? I don't see why you. I don't. Oh, wait a minute.
They're even password protected.
Yeah, I mean, maybe you can. I've never actually run into a case where somebody had like disabled, downloading a Google Drive, but I guess it's possible maybe. Okay, well we can. Yeah, I guess we can just go through if you can't download them.
Yeah. So.
Okay.
That's this one. Okay. So the first one was this. I think that's what I sent you first, right?
Let me see. Let's see. Yes, that one. Yeah. Okay. So yeah.
I think that's here.
Well, it looks like we should probably
Look for flops.
Or look for like this multi-head self-attention, which is I'm just trying to. let's see. Because yeah, this is maybe look for. Okay. Yeah.
Hmm.
All right, so if we look through, for tension mechanisms,
This was around question 10, so
yeah, while you're looking, I'm just kind of looking through some other sources on this stuff, but it's sort of hard to find something that
yeah.
jumps in at the right level.
There we go.
Okay.
Yeah.
Okay. And do they get into? I mean, I guess I don't know, but I wonder if they get into. Yeah, because there's multi-head attention. And I guess there's multi-head self-attention is potentially different still. But the question is asking about like how many flops. So I guess the question is, do they get into like how many floating point operations these things take?
Here are some of the N and the Ds. I don't know if it's just a coincidence or.
Uh, yeah, I mean, I guess I'm not. They may. I guess I don't know this class. I don't know how much they're expecting to work things out from first principles, or if they've kind of condensed it down into some equations. If they've got like it prefigured,
Mhm.
and if there's just some formula.
Yeah, so it's up to here that this section goes.
Okay. Okay, and do they? So I still don't see them getting into, as I understand it, like self-attention is not exactly the same as multi-head self-attention. So if you keep going, do they get into the multi-head
Yeah,
stuff?
So I think they go on to transformer.
Yeah, I mean, transformers are a related topic, as I understand. Um,
Multi-head self-attention. So maybe that's what's referring
okay,
to,
wait.
because it said the previous.
Hmm, yeah. Yeah, so the transformer architecture in figure 9. Oh, if you go back up to figure 9, what do they have there? Okay. Right, 'cause they've got, okay. Yeah, they've got a couple of multi-head attention things in there.
Mm-hmm.
Okay, but that,
So it says.
but you don't see any previous examples of multi-head self-attention in the notes.
So in the notes, we didn't go over because I attended the courses as well. We didn't
Yeah.
do any exercises, which is really weird. The only exercises that we did were at the labs, and those were programming. So
Okay. Interesting.
dimensional
Um,
embeddings, just as queries, but
hmm.
it says queries here and values, keys and values. So I don't know where this is
Right.
coming.
Okay. So I mean, we might have to, yeah, we might just have to like work it out from first principles, um,
Mm-hmm.
like according to uh, that those orders, because yeah, there's a certain number of like matrix operations that you have to do. Let's see, you're doing inquiries.
We're doing inquiry.
Uh, let's see here, doing inquiries. Okay, it's H adds, and the queries, keys, and values are of length D. You're doing inquiries. Um, okay. So yeah, if we go back to those, numbers for, okay, yeah, right, like right here. Or no, wait a minute, that's not, yeah, the self-attention stuff. Okay. Yeah, and self-attention, the queries, keys, and values are all n by d matrices. Um, okay. So let's see. We multiply an n by d matrix by a d by n matrix. And then the output n by n matrix is multiplied by an n by d matrix. Um, hmm. Yeah. And that 8 is referring, is that to a figure 8? Is there a previous figure that they were talking about there?
I look for that, but yeah, I don't know what this means
Yeah, I mean, I assume that referred to,
because this is figure 7.
okay. And there's not a figure 8 after that?
Figure 6. So it looks like they're going in order. Let me check figure 8. Yeah, so this is figure 8. Unless I guess it's the only thing that's referring to.
Hmm. I wonder if they meant 7 because the 7 looked more relevant. Yeah, maybe if we go back to 7 and look at that, because there was definitely something about self attention in figure 7. Okay,
Hmm.
yeah. So self-attention. I mean, yeah, really, that's just looking kind of like a. I mean, that looks a lot like just a multi-layer perceptron, but okay. I mean, I guess we can potentially figure this out. So I think if I understand this correctly, yeah, can you go back down to that next slide? Or let's see, I don't know if they gave you, let's see. Or yeah, or sorry, the slide, I guess, where they talk about the attention complexity. And let me just see, multi-head self-attention. Okay, yeah, so the self-attention. All right, so they multiply an n by d matrix by a d by n matrix. Okay, that I see. I'm kind of on a. Here, I'll link you this guy's site that I'm looking at right now. This is the best reference I came upon after a minute of searching on the general attention stuff. But so I don't know if you want to look at that, but that's what I'm referring to. So I see you've got this n by d matrix that I think is the, what is that? The query, something like that. And then, yeah, the queries, queries, keys, and values. So I see, his terminology is similar to those slides terminology where you multiply Q by the transpose of K. So queries by keys, and that gets you this attention matrix. And then if you scroll down a bit, they've got this attention equation where they then divide by the square root of d sub k, which I'm not sure. Okay. And d is the dimensionality of the tokens. So you divide by a scalar, it looks like. And then you multiply again by v, which is this value matrix, which is n by d. So let's see. So n by d times d by n gives you an n by n, right? And an n by n times v, which is an n by d, yeah, it gives you another n by d. Okay. And okay. All right, and can you let's see. Let me look at this. Scalar and observation and scalar addition both account for one flop. I'm not sure where they're getting exponentiation from n queries and key value pairs. And I'm not, okay, so in the multi-head stuff, I'm not totally sure about, but let's see here. I'm just kind of going down this page to see where they get to. Oh yeah, let me see if this guy, let's see, so that was in 2021. Let's see if this guy has like everything about the multi-head stuff is in a second post. Let me see if he gets more into that in a second post. All right. Okay.
So I realized that this is like question 10 or something from a previous. The first picture that I sent you was a previous, what's it called? Exam preparation.
Okay, yeah.
And I went all the way to question 10.
Wait, sorry. What?
Yeah. It's question 10 out of 11. It's like almost to the end of the exam.
Right. Well,
And
actually, yeah,
if,
yeah. Sorry, go ahead.
yeah, I was just saying because we started at the very end, we didn't start from the very beginning.
Yeah,
I don't know if
yeah,
that
maybe
has anything to do with it.
right, because like question, let's see, 9. Uh, it's the total number of parameters of an LSTM layer. Yeah, so that would be, I mean, that one's a little bit more straightforward. I don't know it off the top of my head, but it's more straightforward. Let me see here. And then 10 is also about attention.
If you
Or
want, we
sorry.
can start from the very beginning.
Yeah, if you well, when you say the beginning, do you mean like the lowest numbered one you sent of
I
those
have the
three?
no, I have the uh pictures or the other
Yeah, I mean wherever you
questions.
want. Yeah, I
I
mean
just forgot to send them.
yeah, we can start wherever. It might yes, if it goes in kind of sequential order, it might make more sense going in order.
That's what I was thinking about.
Yeah. Yeah, I mean, as I mentioned, I've used neural nets a fair bit, but I haven't used these attention architectures. I have a general sense, but I guess I'd be a little bit surprised if they asked this without kind of getting into the details of the models, or unless there's like, I forget. Did you say you guys have like a book or anything that you're supposed to be like a textbook of some kind?
It's no, no textbooks,
Okay.
unfortunately.
Okay.
Yeah, I wish we had a textbook. It would make a
Yeah,
little
I
bit
was
more
just wondering if
sense.
there's some other resource they were expecting you to know, because I mean we can piece this together from internet documentation, but I wasn't sure if that was the most straightforward way or not.
Four, and that's 5.
Okay.
Okay, so it's from. Let's see. And they should be the first 2 problems.
Okay. Yeah. Okay. Yep. I got those.
This is the third one.
Okay. Wish that maybe label these a little bit. This would be easier.
Yeah, sorry about that.
No, that's all right. I'm just putting labels on them. All right. So that's Q3.
So those are the first 5 problems, and
Okay.
I'm working on the next ones just because the pictures that I have are are not popped, and it's very hard to see
Yeah. Okay.
the
So that's
question.
sure. Okay, so let's see here. All right. So let's look at the first couple, I guess. All right, so we have a data set. Points in the 2D plane. Okay.
And I think this is the first one.
Yeah, compute W0 and W1 in terms of x's. So if I understand the way that they're saying it, they want it both symbolically and numerically. Is that right?
I think
Like
so.
they want like both an equation and some numbers. Um, okay.
Yeah, so I think the answer was supposed to be in the format of an equation and with the actual equation equals based on the numbers, if I remember correctly.
Okay. Um, all right. So yeah, we can look through. I mean, I've done plenty of linear regression. I haven't like ever calculated it by hand like this. Let me think about it for a second. Um,
Yeah, so basically every single one of these questions it was on in our lab, but we didn't work it out mathematically.
right. Um,
That's the only problem.
right. Um, yeah. So yeah, it's a little bit weird when they say compute. Yeah, I mean, we could certainly look it up. I don't know if they got into that in your slides. I mean, I can look up how you would. I mean, I know the gist of how you do it, but I've never like implemented a linear regression from scratch. Yeah, so let's maybe look up a little bit how we can do linear regressions by hand, maybe.
So I think this is the formula it's referring to.
mm, well, let's see. Yeah, I mean that's the expansion of the matrix form. But the question is then like you know, when you go to estimate W0 and W1, um, how do you solve for? Okay, so I mean, here's some formulas. I'm not sure if you keep going. Do they like? Let's see if they get into like solving linear regression because I mean, I'm seeing equations for how to do it. Let's see here.
Solving a specific example, I don't think so. Because he said off the top in the beginning of the semester, he said he's not going to work on any mathematical problems. But
Um,
he says like the gist of it.
okay. Um, yeah, I just wonder if they get into the. I mean, because they talk about how to like work with the predictions. If you keep going, I just wonder if they get into like the estimation process because that's really what we're more focused on in this question. Okay, wait a minute. So this is a little bit more like what I was expecting, but let's see. But that's the best values always tell you. Okay, yeah. Can you keep going? Because yeah, I mean, um, yeah. Let's see here. Okay, so okay, yeah. So that's how you get the negative log likelihood. Now we still want to minimize that. So if you keep going, I wonder if they get into how you get the minimum value of that. Okay. Um, okay, so now we're yeah, so now he's getting into this whole process, but like there's going to be an end result to this process, hopefully. Um, yeah, so we have to find this gradient. Okay. So if you keep going, I think towards the end of this slide, we might get the final form. Okay. Yeah, so right, the weight matrix. Okay, yeah, I actually have seen this equation before now that I'm looking at it. And I think actually that might be, let's see. Yeah, so if you want to compute, well, let's see. Yeah, so it's x transpose times x, and then you invert that and multiply it by x transpose and then by y. But like they say, then yeah, to get that inverse is itself kind of a process involving SVD. So I don't know if you
Mm.
keep going. I don't know if he'll end up with a simpler form in the end. Because I believe there is a simpler form for.
That unless let me
That's
check if um, there's a continuation to the regression.
yeah.
No, it just goes to gradient descent.
Okay. Interesting.
So that's all we have from regression.
Interesting. All right. Yeah. So let me take a look at a couple other references just to confirm that
Sure.
this one I'm looking at is correct. But like, um, so yes, sigma y times sigma x squared.
And while I'm at it, I'm just gonna send you the entire um what's it called?
Okay.
The exam prep.
Okay. Oh, wait, let me see what they're calling B0 and B1 here. Hmm. Hmm. Oh, I see. They might be doing this. Okay. Yeah. Yeah. All right. So I think these are, yeah, these two ways of seeing this are equivalent. Yeah, so I mean, we can drum up formulas or come up with formulas to calculate these things. I think the one I found is a little bit simpler to follow than the other. Just double check that. Okay, yeah.
So when it says question 11 next, it's not a question, it's just a prompt to hit finish on our work.
Okay. Okay, yeah. So I mean, for this first one, let's see here. Maybe I can like share my screen and show you this page that I'm looking at. Just put my screen into sharing resolution. All right. So if you look at my screen here, I mean, I can send you here. Let me send you this link as well. This is probably, you know, if they didn't give you a particular formula to use, then, you know, certainly you can use, I guess, whatever. Let me pull up the question. There it is. Okay. So there's the question. There's the equation. So like, yeah, I mean, what they're doing here, let's make a new text window for now. I can put this on the whiteboard or something. Actually, here, you know, yeah, let me do this on the, why don't I do this on the Wyzant? Why don't we work through this on the Wyzant whiteboard? We haven't used that a whole time, but it's probably useful for this. Have you used the whiteboard much at other times? I mean, I'm sure you're familiar with the.
Yeah.
I'm going to put it on board 2 because whenever I use board 1, it seems to, like, if you try to download it later, it gets corrupted. So I'm going to, here, I'll put the question on board 2.
Okay.
And then, oh, maybe I will. Okay, there it goes.
And I did send the entire prep via messages.
Oh, okay. Okay, so there's okay, yeah, so you can see that. And here, let me put in this formula. So, you know, they're on this page, they're using kind of like slightly different terminology, but it works the same way. So, you know, they're using M for the slope and B for the intercept, which is fine. So basically, here, let me grab my little drawing tablet. So just to kind of put things in their terminology, they're calling, let's see, they're calling the slope W1. So that's going to be M, and W0 is B, right? And so, yeah, there's a few different formulas you could use for this, but presumably, yeah, basically, well, okay. So here, let me give you a different set of formulas, because this formula, the only thing that's a little bit weird about it, I mean, it is probably the easiest way to do it. The thing that's a little bit weird about it is it uses one of the calculations and the other calculation. So if you don't want to do that, I've got like another reference. This is not maybe as good of a, like, it's not spelled out as nicely, but here, let me, or actually, I'll send you this link as well.
You guys would be just the answer of the W1 equation, right?
Exactly.
It won't be the entire equation where you have to cancel out.
Well, I mean, yeah, yeah, like if you were doing it, you know, yeah, if you were doing this in real life, I think the only practical way to do it, yeah, would be to like first get the value of M or W1, whichever you want to call it, and yeah, and then plug that in. But if you want to just do it directly, I just pasted another page in the chat that's got a different formula. Here, I'll put these down here now. Let's see what they're calling B0. Let me make sure I get this right. Yeah. So that's what they're calling like W0, or what you're calling W0, and this one
Mm-hmm.
B1 should be. So this one should be equivalent to the W1 equation. Yeah. So that might be a little bit better way to do it. So basically, um, so if we put these into, so like, let me just write these like mathematically. So B0, or like, right. I'm kind of like, more like you're used to. So sigma y sigma x squared. Let's see, what is that? Minus sigma x sigma xy, and then all of that over n sigma x squared minus, this is sigma x quantity squared, which is different. Okay, so that would be that. Now this one for B0 or W0, or sorry, a B1 or W1. Actually, I'll keep it in the terminology of that webpage. So they called it B1. So it just depends on what you call these things. But let's see, that would be the same, right? So sigma, or n sigma xy minus sigma x sigma y over, let me make sure. Yeah, okay, and that's n sigma x squared, yeah, minus sigma x quantity squared. Okay, so, and that is, I believe, yeah, these should be the same. Right, these are the same here. I just want to make sure, writing it out, that they are the same. But yeah, okay, so yeah, if you were wanting to just express this symbolically, now I guess if you're doing it in terms of, well, okay, yeah, I guess if you're doing it symbolically, that's probably about all you can do, is use these formulas, right? So I guess this would be, W1 equals, this whole thing, right? And W0 equals this whole thing, right? So I think in terms of the symbolic way to do it, that's pretty much it. Now, to do it numerically, you just have to kind of set up like x1 equals 1, x2, I don't know if we're going to run out of space here for you, x2 equals 2, x3 equals, what is that, 3, and y1 equals 1, y2 equals -1, and y3 equals 2. So I don't know if you want to like do you want to work out the numbers for this? I mean, you would basically just be plugging these numbers into those equations, but we certainly can work through that if you want to. What do you think?
Oh, so it says, so I just realized it says in the equation, in the problem, we don't have to do it symbolically.
Yeah, I wasn't sure what they,
We just have to
when they
find the
say computer,
values
yeah,
of W1 and 0.
right. So if you think that's what they're wanting, yeah, I wasn't, when they say like in terms of, the X's, I wasn't sure if they meant like you had to actually do it symbolically and numerically, or just numerically. But yeah, so I mean, either way,
Yeah.
like these would be the equations that you would use, I guess, unless they give you a better way to do it. And so, I mean, did you want to work through the actual calculation, or do you feel like you have that part?
Yeah.
Okay, all right. So I'm gonna,
I do want to work. Yeah, just in case.
okay, yeah. So if we go down, well, all right. In that case, so I'm gonna have to go. Let's see. We might have to. Why don't I just because we're running out of space on your screen. I mean, you can. If can
So
you
just
scroll?
board 3.
Yeah, I was trying to decide. Yeah, why don't we just do that? Why don't I just start it over again on board 3? Yeah, with just the I'll just put in the critical information. Why don't? All
This
right.
remains, right?
Yeah. So here, well, let me clip like this stuff from this page, and we'll put it on next board. It'll get a little bit of
Okay.
extra garbage on there, but it'll be fine, I think. Okay. So yeah, if you go to board 3, I'll just put, there's going to be a little bit of extra stuff on there, but that's okay. Because I wasn't able to clip it exactly. Okay. Actually, I can make that a bit smaller. It looks like it's. Oh, are you still there?
Yeah, I accidentally hit the back button
Okay.
instead of hitting the.
No worries. Okay. Yeah. So that's. All right. So that's going to be hopefully not too small on your screen. All right. So yeah, if we do this, so then basically I cut off our beta, or you're calling it W1. So here, I'll do this in a separate color, actually. Let's do this in like green, maybe. All right, so you're calling it W1 is equal to N sigma XY minus sigma X sigma Y over N sigma X squared minus sigma X quantity squared. Okay, so that's going to be W1 equals, all right, so N is, I guess, our number of, let's see, that would be our number of elements, I guess. So that would be, what did we say? 3, I suppose. So it'd be 3 times, so the sum of all our xy's, well, xy, oops, xy1 would be 1, xy2 is -2, xy3 is equal to 6, I think. 1, -2, and 6. Yeah. All right. So the sum of our xy's is 6, -2, and 1. So that's 4, 5. So that's, I think, 5. Right. Minus, and then sum of our x's is 1, 2, 3. So that's 6. Times sum of our y's is 2, I think. 1, -1, and 2. So that's just 6 times 2. And then that's 3 times sigma x squared. So our x squareds. Wait, what now? Sorry. I have my battery, my headphones gave me a low battery thing. And
Oh, is it 36?
let's see. Well, it should be, because it's
Oh, it's
the,
from each. Okay.
yeah, it's the sum of the, yeah, it's a little bit tricky because the sum of the squares of x is different than the sum of x squared, which is our next thing to calculate. Yeah, so the third square is 9, right? So yeah, the sum of those 3 squares is, I guess, 14. It looks like. Minus, and then yeah, it's going to be minus their sum, which is squared. So then yeah, 1 + 2 + 3 is 6, minus 36, right? So then you just have to do some arithmetic. So that's 15 minus 12 over 3 times 14 is 42 minus 36, which it looks like is 3 over 6, which is 1/2. And actually, let's think about this for a second. If we draw this, X is 1, 1, or x1. The first point is 1, 1. Second point is -1, -2. So that'd be like here. And the third point is, oh, wait, sorry, I screwed that up. Sorry, I misread those. It's 1, 1, and X is 2, and Y is -1. So that's here. Okay, wait a minute. And 3, oh, wait a minute. Is that right? 1, -1, and then X is 3, and Y is 2. Okay, maybe that is right. Okay, so that's not a very good fit for a linear regression, but I guess it is vaguely consistent with having a slope of 1/2, because those 3 points are kind of not a very well fit by a line. But okay, we'll go with it. All right, and then for our intercept, our W0 formula is, what is that? Sigma y, sigma x squared, minus sigma xy over n sigma x squared minus sigma x quantity squared. So that's going to be, all right, so sigma y we can figure out. So that's 1, -1, and 2. So that's 2, we said. Sigma x squared we had already, which is, we said 14, right? So 2 times 14 minus sigma x. So that was 6, and yeah, sigma x was 6. And sigma xy we said was 5. I think, right? Yeah. Okay, and then that's over 3 times sigma x squared, so that's still 14 minus, and then that sigma x squared is still 36, sigma x quantity squared. So does that work out? W0 equals 28 minus 30 over 42 minus 36. So that'd be minus 2 over 6 equals -1/3. So if we did all that arithmetic right, I think that's your answer.
Yeah, so I don't know if this is part of it, but one of my classmates got the answer, and
Okay.
for some reason W1 was 1 and W0 was noise. Do you know what that means by any chance?
Was noise. I'm not sure what that is supposed to mean. Because I mean, yeah, you're not going to get an exact answer because this doesn't perfectly fit a regression. Let me actually,
Right.
I'll just quickly punch this into Excel. So 1, 1, 2, -1, and 3, 2. Here, I'll like share the screen while I do this. Okay, yeah. So if you look at Excel, there's our 3 sets of numbers, and if we just do a quick linear regression on them, let's see. Let's just here. Easiest way is probably to insert a. Oh, how do we do this? Scatter plot. And so there's our points. And then if we, let's see, I have to remember how to do this. There's definitely a way to like, okay, there we go. Chart options. There's definitely a way to like add regression lines to the chart. Let's see. Well, all right, let's do it this other way. I mean, I was just doing Excel because it's quick. We can also just do a Actually, this might be the better way anyway. There is an analysis function in Excel to just do data analysis, regression. Okay. Y range is here. X range is here. There's no labels. Yeah, we'll just put in a new worksheet. Okay, that's probably easier than trying to remember how to do it on the chart. So intercept, okay, yeah. Intercept is negative 1/3 and slope is 1/2. So that did calculate out correctly.
Okay.
Negative one, yeah. So just double checking that against
Mhm.
Excel. But I think that's right. So yeah. Yeah.
Oh, I
Negative-
think I see what they mean.
negative 1/3 and
I-
1/2. Yeah.
Yeah, maybe negative 0.3 is noise. Like that's the value of noise, but I have no idea.
Yeah, I don't know why they mean no. I mean, they're in a regression that where the line does not perfectly fit the points, which would be the case here. You are going to have residuals, like you're going to have residual variance, but I don't think that's what they're asking back in the original question. If I
Okay. Yeah.
pull up the original question, but again, yeah, because you can get an actual value for W0 and W1. You would just also have some noise left over.
Okay.
So really, you would have like an error term, which I think is maybe what they're saying, but I'm not sure. Okay.
Yeah, it was an E. So yeah, I'm not too worried about the noise. Let that be the only one that's
Right.
uh
Yeah.
that's the least of my
Okay.
worries.
Right. Okay. Well, I mean that. Yeah. So that's one of them down. Now, I mean the next one is significantly more involved because we're doing a lasso model. I'll stop sharing my screen so I can take a look at yours. So again, I'm familiar with, I can do a lasso like in stat software. I know what the idea is.
Mhm.
Write the batch gradient descent update for W1, 0 and W1 in terms of.
Okay, so this thing gradient descent. Okay, that's exciting.
Yeah, well, it's gradient
So I
descent, but
remember
it's
seeing
gradient descent for lasso. Um, so I don't know if they got into that at all for the lasso technique.
they probably did, just didn't call it lasso.
Okay.
Because I remember the I don't know if it's called lambda or something.
Yeah, the lambda
But we had
parameter.
like
Yeah.
a equation that uses. I mean, I doubt it's this one.
Well, let's see. Okay, wait a minute. Oh, yeah, actually, so let's see. So the loss is blah, blah, blah. And regression using this loss function is called lasso regression. Okay, so write the batch gradient descent update. Yeah, so I think let's see. Yeah, that is lasso regression for that loss function. So I think that is a useful thing. Let me actually grab that. Hang on one second before you scroll. Okay, yeah, you're good. I just wanted to copy that loss function and put it somewhere before, because that's not the kind of thing I know just off the top of my head. I'll put that on board 4. And then I just have to, either from your notes or I have to find or remember like how we write the gradient descent batch gradient. We have to write the batch gradient descent update. So let's see. So we have to find the. Oh, wait a minute. I see what you're doing. Let's see. Gradient descent. Okay, that might actually be it. I'm just let me just confirm the formula here. Because again, I've sort of done this, but not exactly. Oh, wait a minute. What are they saying here? Just add lambda w to the gradient vector. Let's see here. Oh, wait a minute. So that's, I see. But this is looking at so that's very similar to the loss function. I'm just trying to work through x minus y. Yeah, let me see exactly how they asked the question. Write the batch gradient descent update in terms of the x's and y's where the learning rate is eta. This is, yeah, batch gradient descent. Okay. Yeah, so do they have a generalized formula anywhere in here for batch gradient descent? Because I vaguely have seen it before, but I don't remember off the top of my head.
Is that it?
Yeah. Okay. Yeah, let's take a second for that. Let me just work through what they're doing here. And they're saying, let's see, what do they say? They say they want the batch gradient descent update in terms of I'm missing where they yeah, okay. So I think what we want is yeah, I mean that sort of roughly makes sense to me there, but so we need the partial derivative, right? I mean, we need the gradient of that loss function. Actually, let me just look for the batch gradient descent for lasso. Hmm. Oh. Okay, I'm not. Let's see. I mean, yeah. So the general form of that gradient like makes sense, but the question is, how do you get the gradient of that loss function? Um, and let's see. Just looking through like various examples here. I'm just trying to okay, if you go back to, let's see, if you go back to where that loss function for lasso was, which would, oh, wait, I think you might have just pass it, or was that a different loss function?
Oh, I might have passed it.
Yeah.
No, because I think it was 1.5.
Yeah, it goes further. Yeah.
Here it is.
Right. Linear regression using this loss function. And they don't go on, if you go to like one later slide than this, do they go on to give us or maybe another slide after that? Do they give us how to? Oh, okay.
Okay.
Okay, let's go one more slide. Maybe one more. Just looking to see if they do the. Okay, yeah. So this is okay. All right, this is what I was getting into. So, yeah, the lasso loss function is not differentiable. So, gradient vector we can use for gradient descent with the lasso loss function. Okay, so if you go one more slide, I mean, that might be a relevant formula, but let's see. Okay. Okay, so that's the loss function, but okay, that's, yeah, then I think we're going bad. So go back up one slide there, if you don't mind. Just looking to see. Okay, so subgradient vector. Let me compare that to the okay. Yeah, so if I'm reading it right, I think we can use that formula there. Let me snip that here. I think we can use that formula there as the gradient. Or as a substitute for the gradient. In which case, here, let me Yeah. So if we go back to so if you go back like up to where it first starts talking about like let's see, yeah, up towards the beginning of this slideshow, I guess, where they're giving you kind of the general formula for the weight update based on the gradient. I think you can
All the way up.
pretty high up. Yeah, let's see. It was like yeah, right here. So basically, your weight update is your weights minus eta times your gradient of your loss function.
Mm.
And so, yeah, if I'm okay, let me compare that. Give me 1 second. Okay. Yeah. So basically, because that gradient that they're talking about there, which I think is the gradient for I think they're just talking about this for regular regression without that regularization. It actually, let's see, is very similar. 1 over n x transpose times xw minus y plus, lambda times sine of, okay. Yeah. So really, the gradient comes out very similarly. So I think, so if you want to go back to the, or actually, hold on, don't do anything yet. Let me just clip that one little formula here. Okay, yeah. So if you if you look at board 4 on the whiteboards, if we kind of put this stuff together, I think you should be able. So basically, what that implies is, so W would get W minus eta. Well, I don't need to rewrite the gradient part of the equation again. So our gradient, or our substitute for the gradient, would be 1 over n x transpose times x w minus y. Let's see, plus lambda sine of w. So then if we did that, if we did that for the numerical example they give you, let's see, where was it? Just trying to find, okay. Actually, here, let me just clip that and put that on the screen as well. Okay. Yeah, it's going to be, all right, that should be pretty good. I think we can both see that. You might have to scroll down a little bit if I keep going down. I think it'll let you scroll downwards if I kind of run below where you can see. But so that would be, let's see. Well, okay, so I guess the trick is, we don't have existing weights, so I guess the weights are still just going to be W, but X is going to be 1, 2, 3. Y is going to be 1, -1, 2. Whoops. 1, -1, 2. And we said lambda equals 0.1. Or sorry, no, eta equals 0.1 and lambda equals 0.01. I guess I don't need to rewrite those really. Okay, so I think that would be W gets W minus eta's 0.1.
Yeah.
Yeah. Times 1 over n, so that would be 1/3. So X transpose, well, actually, let's see. They're thinking of W. let's see, x times w. So they must be thinking of x as 1 by 3. So actually, I guess I think they're thinking of like these as, so these would be like the transposes, I think. Let me just see. X trans. Well, actually, no, I take that back. Because it's going to be minus y. I have to think about like which way they're thinking of orienting these things. So x's, let's see. Yeah, I guess x's would typically be. Yeah, actually, so I think this would be x transpose, but that y would be just as it is. No, wait a minute. Let me think about this. No, I take that back again because we've only, yeah. So that wouldn't be x transpose. That would be just regular x. So would that be right? Excuse me. I'm just trying to think about like, let's see, x times, like how they're thinking of orienting these. So because we want if our weights are well, this is lasso of regression. I guess actually, I guess our x's here. Let me do it this way, because really, I guess they would be expecting. Yeah, they're expecting an intercept. So really, our x's, we'd have to do it that way. We'd have to put an intercept in there. So really, our x's would be this.
Mm-hmm.
Because it would have an intercept in it. So then your weights, I guess you'd be expecting. Let's see, if you're doing x times weights, then your weights are going to need to be. Yeah, your weight's going to need to be 2 by 1 for that to work out. So weights. Here, I'll put that up here. Weights equals, W0. W1. So they're thinking of weight as being, this is always like, everyone kind of notates these differently. So you have to think about whether they kind of think of these things as being horizontal or vertical vectors for the matrix math to work out. But yeah, if we do x, so that's a 3 by 2 times a, oh, wait a minute. Nope, did I screw that up? I did screw that. Yeah, no, the weights would be vertical. Sorry. Yeah, so the weights would be vertical. Right. Okay, yeah, that makes more sense. Because it'd be a 3 by 2 times a 2 by 1, which would give you a 3 by 1. Yeah, okay, that works out. All right. So it'd be 1 over 3 x transpose. So that would be 1, 1, 1, 1, 2, 3 times, so x times w would be 1, 1, 1, 2, 1, 3 times, well, whatever W0 and W1 are, minus 1, negative 1, 2, plus lambda, which is 0.01, times sine of w, which I guess would be, well, actually, we don't know what it is, so that would just be sine w0 and sine w1 close my parentheses there. So it's a little bit weird because they say like numerical application, but they don't give you any initial values of your weights. So I don't know how to solve it out more from there. You know what I
You
mean?
had to use the
'Cause,
one from the previous, the question number 1.
maybe if that's what I wouldn't have thought that those questions go together, but
I don't think that, I mean, unless it's literally the biggest coincidence ever that they use the same.
well, those are kind of generic like variables that you would use for this kind of math. So I was just assuming that. But yeah, if you think they're, I mean, you know how they think better than I do. So yeah, if they think you want to do it based on our old W0 and W1, we can do that because we found W0 was negative 1/3. So that's negative 1/3. And I think the other one was 1/2, right?
Mhm.
Yeah. I'm just going to write that as 0.5 for space. Okay. Kind of mixing fractions and decimals. So yeah, I mean, I guess you could do it then. So that would be like W gets, so that's that, which is negative 1/3 and 0.5 minus 0.1 times. All right, so 1/3 times, let's see. Well, let's do the matrix multiplication and then do, yeah, because the scalar multiplication we can do wherever we want. So if we work all this out, I'm just going to, here, let me, am I sharing my screen? No, I'm not. Let me just kind of share my screen and like pull up a MATLAB to do this because that'll be a quick way to do the matrix multiplication. I'm amazed that they would make you do this like by hand on a
Yeah.
test, but maybe, okay, so if you can see my screen, I'll try to, so that doesn't, MATLAB sometimes freezes for some reason, but it looks like we're okay now. All right. So let's see, we can just maybe do this all in one go. So, all right, so we can do like minus 1/3 0.5 minus 0.1 times, all right, and then we've got 1/3 times, so that'd be 1, 1, 1, 1, 2, 3 times, then we're going to have to do some fractions. So that's another level of parentheses. So that'd be 1, 1, 1, 2, 1, 3 times W0, or just the weights again. I mean, W0 and W1. All right, so that times that minus 1, negative 1, oops, negative 1, 2. Okay, and then close the parentheses around the multiplication and subtraction. Just make sure. And okay, I think I'm closing that. And then plus 0.01 times, and then the signs of the two weights. So that would be negative 1, 1. Let's see. So that's closing that parentheses. Actually, I don't need the parentheses around this. That's just a matrix. And then this should close around the 1/3 times. Yeah. So, I mean, it's a long way to go for getting that. It looks like they each
Yeah.
decrease by, actually, let me just look at this part. So I just want to see. So it'd be this part here, I guess. Yeah, okay, maybe that's what maybe we're supposed to like see this without thinking about it, but it looks like basically this term. So let's see, if we kind of break this down into terms, it looks like this term here. Yeah. Okay, that's just some random numbers. But then when you multiply that by, 1, 1, 1, 1, 2, 3, you get basically 0. I mean, that's essentially 0. So it looks like this whole term drops out basically, and then you just get 0.01 times the sign. So, and that, I guess, I mean, honestly, like that sort of makes sense, because if we're going with the weights that we found in the previous question, they would already be like, the error is already minimized basically, right? Like, because this whole term is basically kind of the error in our regression, not accounting for the regularization, but the error is already essentially 0 because we've minimized it as much as we can. So, I mean, hindsight is 2020, but like, yeah, that sort of makes sense in retrospect, that would, like, this term would basically be 0, and then yeah, and you'd basically just be adding, and you'd be subtracting, or I guess you'd be adding 0.001 to, because you're subtracting 0.1 times 0.01 times the sign, which was negative, which means you're adding a positive 0.001 to your top number and subtracting 0.001 from your bottom number. So,
would doing it by hand be hard, or because I don't think we're allowed to use MATLAB?
Yeah, it would be hard. I mean, I don't know if you're allowed to use like regular calculators or whatever. It would be hard, except for the fact that I guess maybe, and if I had been doing this math recently, maybe I'd have thought of this. But like, if you recognize that like this whole term is 0, right? Like, you would just have to know that by virtue of the fact that like you've already minimized the error in the previous equation. So then, yeah, then your weights are just going to be, are just going to be minus, or let's say like minus 0.3333 and 0.5 minus 0.1 times 0.01 times minus 1 and 1. If you can scroll down a little bit more, so that basically just gets 0.3333 and 0.5 minus 0.001 times negative 1 and 1, which is going to be equal to 0.3333, 0.5 plus, or let's just keep it at minus, I guess minus, point, or let's see, minus 0.001 and that's going to be plus 0.001. Right, which gives you what MATLAB gives, which is 0.3323 and 0.4990. Sorry, that's a minus 0.3323 and a 0.4990. Oh, and that should be, yeah. I lost my minus signs here, but that's minus and minus. Okay. Yeah. So, I mean, yeah, under the assumption that they mean you to update the weights from the previous question, I guess that makes sense. I mean, you wouldn't normally run a lasso regression after running a normal regression, but sure, why not? So, yeah, I guess that's what they're going for there.
Okay. Yeah. Yeah, a lot of us weren't sure either. So
Yeah, I mean, that was a good
regarding
thought that
anything.
they might be thinking, yeah, they might be, again, that's a fairly big assumption, that it's relying on the weights from the previous question, but I think you're right that that's the best idea we've got. So yeah. Okay.
Okay.
All
Yeah.
right. So does that one make sense? I guess.
Yeah, I guess.
Yeah. I mean, it does. That does give me more confidence that we got all the symbolic math correct, because it does kind of make sense when you get to the end of it. But it is a little bit of a complicated process for sure. And yeah, like all that stuff about the lasso loss function not being differentiable is I don't know. I mean, that's a lot of math to know off the top of your head, but I guess they did give you the equivalent. Okay. All right. Well, anyway, anything else on that one, or you want to keep moving on?
Keep moving on. I mean, if we
Okay.
have time, because they do take a lot of
Yeah, this stuff is. I mean, I'm
time.
sure. Like again, I've never offended if you like somebody that is, sort of like a PhD in computer science who works on this stuff might know the linear algebra like off the top of their head. So if you find such a person, you might be able to go through it faster
I
with them.
tried.
Yeah.
Yeah, I tried. Nobody knows except for you.
Well, yeah. I mean, and I, like I said, I can work it out, but it's yeah, like there's not that many people around that know this stuff probably off the top of their heads, because
Yeah.
you know most of those people are actual professors in computer science probably, and you people that use this
To be
stuff
honest
usually
with
just know how to
you,
use it. Yeah.
yeah. To be honest with you, I don't think the teacher knows either. It's just he's asking, knowing that the students won't know, which
Yeah, I
I
mean,
encountered a lot at this university.
that is certainly possible. I mean, yeah, like this is, again, if you were like a graduate student in, like, if you were doing PhD level work in this stuff, yeah, you probably would, and like writing papers, about
Mm-hmm.
the mathematics of these processes, then you'd probably know this stuff, and your faculty advisor would probably know this stuff. But most people who do this on a day-to-day basis just know how to write the code. They don't worry about the math beyond the fundamentals, because the math gets so complicated.
Yeah, and that's what we thought. We thought all of us thought that none of us were gonna get any like. He said that there wasn't gonna be any math involved on the final exam. That was the first
Yeah.
words that came out of his mouth. So
Yeah,
I don't
looks
know
like
what happened.
looks like that was not the
Yeah.
case. Yeah, because I've certainly had some people like, well, you and I did this, right? Like you and I had to do the thing where we kind of wrote, a gradient descent, but they sort of usually give you the math and then say, all right, write some code to
Yeah.
implement this math or whatever,
Yes.
and that's reasonably fair. I mean, again, it's not something most people have to do day to day, but it's fine. But anyway, okay. Well, let's see. So I think let me take a look. Like number 3 doesn't look like it's too bad. Let me just
Maybe
see
we can
here.
finish on number 3.
Yeah. Well, okay.
And then I'll
Yes.
just schedule another lesson or two. I know that Thursday. Yeah, I'll figure out when we finish.
Okay. Yeah. Yeah. At least the first part. Let's see. Okay, yeah, parts of this are not too bad. All right, I'll put this on like board 5 here. I'll clip the question and put it on there, and we can walk through it. The writing the equations is going to be a little bit tricky. Not too bad. I don't think the thing that I'd have to think about.
Think I know where it is. Yeah.
Oh yeah, if you have so the only thing that I don't like this is a little bit more like because MLPs are not too well. Let's see. MLP for
That one I
regression.
know I have on
Yeah.
the slides.
Okay. Cool. Because yeah, the tricky part is writing the equation for the ReLU, which like I know what it does, but how you would notate that mathematically is a little bit weird
Yeah.
because it's hmm,
Yeah.
yeah.
So
But
I
yeah,
don't know. Let me just
we can see what they say in the
yeah, computer
notes.
output. Oh, okay. Let me just see where it starts.
Yeah, and I'm not.
Nothing here.
I don't
Nothing
know when they're
here.
actually now that I look at this, when they say an MLP for regression,
Yeah.
but two
This is
outputs.
the
Oh, I
only
guess that makes
MLP we
sense.
have.
Okay.
And these are
Um,
the only slides with the O's and the X's here. I think. Well, never mind. But we'll come back to that.
yeah. Um, yeah. What I'm trying to think about is if it's an MLP for regression. So I guess what they're saying. Hmm, it's just a little bit weird when they say an MLP for regression and two outputs.
Mm-hmm.
Um, it's a little bit odd because if they're saying like do an MLP to do regression, like to just calculate a y from a set of x's, that would really just have one output. But if they're saying like do an MLP to calculate a regression set of regression parameters, which I guess you could do, that would be two outputs, but that would be a little bit strange. All right. Anyway, I don't think it really matters because, yeah, it doesn't really matter what the MLP is for. I think the main thing is the structure of it. So,
Mm-hmm.
I mean, I think well, maybe yeah, we can start with like the diagram, and so I mean, the diagram should be pretty easy, right? Because, um, let's see how they just wrote theirs basically. Um, they did theirs vertically. I feel like well, we have more horizontal space than vertical space, so it might be easier to do it like horizontally. But
Mm-hmm.
basically, you've got three inputs. So there's your three inputs. Now I don't know how they're expecting you to draw this. If you can do drawings in software or whatever, but
Yeah. I think each one should have like the arrows coming out to each one, right?
right. So you'll have like hidden layer one, hidden layer two, just
That
three
was
units.
what was I confused on a little bit. If it should be on one full line or on different on separate like this.
Uh,
Um, do you mind if we go to the bathroom real quick?
sure. Yeah. Yeah. Take your time.
Sorry about that.
No worries. Okay, so I mean, I think that's your basic for an MLP. That's your basic network diagram, right? Where you just kind of you basically connect each unit in each layer to each unit of the next layer.
Mm-hmm.
So I mean, that part's pretty easy. Now for the equations for the forward pass, you want to go back to your slides for a second? I just want to see how they notated it because they like have the general gist of it, but they probably use their own notation. Didn't yeah? I think you went past some equations where they talked about. Okay, yeah. So it looks like okay. Let me actually snip that. How they do that because let's see. Oh, Nate. Okay, here. Let me snip that and then we can talk about it. Okay, yeah. So I'll put that on the whiteboard, and so that's with like one hidden layer. Or maybe put that up here or something. Yeah. Okay. Looks like you can still see that. So, I mean, basically, to get I don't know if they had like notation for this. I mean, you can just make up your own, but like, yeah. So basically, hmm. All right. Well, this is not. Yeah. So this is not yet worrying about. Hmm. If we forget about the ReLU for a second, you could basically say like, all right, your hidden one output is going to equal um, your x, yeah, times your weights. I don't know why they put the weights. Like I would normally put these as subscripts, but whatever. Maybe that's just a. And then times your betas. Oh, actually, I think I see why they're doing that because that's to distinguish it from like a row or whatever. All right, let's just do it their way. So, whoops. W1 plus bias or whatever 1. And then you just kind of do the same thing like what they're doing for their output, you would do for H2. Where you just say you take H. Actually, I guess why don't I use their notation for these subscripts also. So do like H1 and H2. So that'd be H1 times the second set of weights, plus your betas 2 or your biases 2. And then finally you'd have output, which would equal H2 times weights 3 plus biases 3. So that would, be, that's just kind of extending that notation a little further. Now, the thing that makes it a little bit tricky is the ReLU activation function. Oh, sorry. You can probably still hear me. I think my headphones just cut out because they were giving me low battery. Give me 1 second to swap them out.
Sure.
Okay. I think I'm back. Can you hear me okay?
Yes.
All
Yes,
right, cool.
yes.
Sorry about that. Yeah. Usually I can make it through a whole session if it starts giving me low battery, but every once in a while it craps out. Okay. So yeah. So did they get into like how they notate ReLU activations mathematically? Because
I mean, I can. go to the slides. Yeah, unless do
Sure.
you still see my screen?
I can still see your screen.
Okay.
Let's see. Okay, so there they. Okay, so I guess we can keep going there. Okay, maybe they're just. Yeah, I mean, maybe they're just expecting us to like apply a note, like give the ReLU like a function notation, and
Mm-hmm.
not to actually calculate it, because a ReLU would basically, I mean, usually for a ReLU, you would have, its value would be zero if the input to the activation function was zero, and then it would be uh, it would be, I think, just equal to its input for any inputs greater than zero. Although you can get yeah, there's also like a version with which I can't remember the name of. Oh, a leaky ReLU. Yeah, a leaky ReLU has a slightly different gradient, but anyway, or a slightly different definition. But okay, so if you keep going, do they talk about ReLUs anywhere in particular, or not really? Oh wait, let's see. Yeah, that's another way to say it, I guess, is max x and zero. Yeah, okay. If we scroll down, do they give us any other notation? Um,
Wait,
oh
wait,
wait,
wait. I think I went too far.
yeah, yeah. So if
So
you
this
just
is where we
go,
started.
yeah. So there's a graph of what the ReLU function looks like. So that's fine and all. Okay, that's fine.
Another graph.
Yep. Okay. Um,
Unless it's this one.
yeah, and that's another different function. Okay, so it looks like they kind of stopped talking about ReLUs. So yeah, I don't think they're giving any like particular notation that they're expecting you to use.
Mm-hmm.
Um, so I mean, if that's the case, I mean, I guess you could like if you want to go back here, you could here. Let me like erase this or move this over a little bit. Let me see if I can. I can like select this stuff and move it over some. Yes, okay, that worked exactly as I hoped it would. Okay, so like you could just yeah, I mean, I guess you could just basically sort of sort of say, all right, we're going to pass, just call the ReLU function R or whatever. You
Mm-hmm.
could just like wrap each of these in an R function, because really, and then you could like define that, I guess, somewhere. So you could say like R of X equals X for X. Oops. Uh, X greater than 0, 0 for X less than or equal to 0. I mean, you could do it like that, I suppose. Um, and that would be, I guess, how you'd write it.
Mm-hmm.
Okay.
I think he's just gonna want us to write out ReLU just to
Yeah, I
know
mean,
that we know
you
how to
could,
do it.
yeah, right. You could just spell out ReLU instead of calling it R. I just did that for brevity, but you could also just write ReLU. Yeah. But yeah, as long as they're not expecting you to like notate the individual equations in any particular way. So that would do that, and then you would be computing an output. Okay. So then I guess you would just kind of like make up a bunch of, you know, weight matrices and bias vectors.
Mm-hmm.
So you can just calculate it. Yeah. So, oh, I guess I see. I think I see why they're doing two outputs, although it's a little bit weird. I mean, usually, because I guess they're doing two outputs because you've got two inputs.
Mm-hmm.
Yeah, I guess that makes sense. Um, I mean, basically, this is just a matter of like doing some matrix math. I mean, so they just say like generate these yourself. So I guess what you'd have, right? So if we just think about like what sizes things have to be, so we've already got the size. So X is, 2x3. Actually, I should put an equal sign there. I should put like a colon because it's not equal to that, but it is that size. X is 2x3. Weights 1 would have. Well, this gets a little bit weird, I guess, actually. No, actually, I don't know why they're doing. I take that back. I don't know why they're doing two outputs. All right. Yeah, I don't know why they're calling this because yeah, we'd have to do these each separately, I think. So weights 1 would be 3x4. Right.
Mm-hmm.
And then bias 1. So let's see. Bias 1 would have to be let me think about this. So X is coming in. It's like a 1 by. So really, each X is going to be a 1 by 3. That's going to multiply by a 3 by 4. That'll give you a 1 by 4. So let's say these are. Excuse me, 1 by 4.
Bless you.
Thanks. And then yeah, your weights 2 would be would have to be 4 by 3. 4 by 3. And that's your biases 2 would have to be then 1 by 3. And then your weights 3. That means it'd have to be 3 by 2. And your biases 3 would be 1 by 2. Okay, so what you'd really do, and again, I guess you can just, I'm surprised that they would make you do this much linear algebra, just to do it sort of quickly, because I know we're kind of at time and I do have somebody else in a few minutes, but, well, do you have somewhere to be right now, or do you have a couple more minutes?
I'm gonna have a couple more minutes, but if you want, we can stop here and then we can just finish it next time we meet.
Sure, if you want to, yeah. I mean, basically, it would just
Yeah.
be kind of picking some random values and like doing the multiplication. But yeah, we can do that another time because that's not super
Okay. Yeah.
critical, I guess. Okay, but I mean, yeah, it's really just going to be like picking some random values and doing some matrix multiplications and additions. But yeah, we can do that next time.
Yeah.
Okay, cool.
So this Thursday I have an exam,
Okay.
but I should be free after that.
All right, sounds good. Let's see. I'm not sharing my screen right now, right? I just want to look at a couple of other messages and see, because I think I had some other people who had spoken up for a time. So let me just make sure I don't. Okay, so this person's doing 2 Pacific on Thursday. So what time did you say your exam was done?
Let's see. I don't think I have a time yet.
So let's just say after 5 p.m.
Okay.
because I'll send a message if anything changes, but yeah.
Okay, so let me look at my Thursday schedule.
Actually, let's do after 2 p.m.
So you think you'll be done by 2 p.m. Pacific?
Yeah, I think so.
Okay, so let's see. Do I have time then? Yeah, because Thursday I'll have somebody else at 2 p.m. Pacific.
Right.
They'll probably be done in an hour. Actually, let me go ahead and pencil them in and see what that gives us in terms of free time. All right, so that would give us, yeah, so then my next appointment, I believe, is not until, yeah, is not until 5:30 Pacific. So what that would leave us is, yeah, we could do like 3:30. Yeah, we could do like 3:30 Pacific if that works.
I mean, if it works, but would you rather do it on Friday? Do you have availability on Friday?
Friday, I could do, yeah, I could do like 2 o'clock Pacific on Friday. I've got about an hour and a half window then, if that's better for you.
Yeah.
All right, so
Sure.
2 Pacific on Friday.
Yeah. And a 1.5 hours.
All right, sounds good. All right, I'll put you in for 90 minutes starting at 2 Pacific on Friday. All right, cool. Yeah, anything else?
I think that covers it for today.
All right, awesome. Well, in that case, have a good rest of the day. Good luck with that exam on Thursday, and I'll see you Friday at 2 Pacific.
See you Friday.
All
Thank
right,
you.
Thanks much. See you then.
Okay.